Okay, so now we're going to talk about weight and a little bit, in fact, the difference between weight and mass, or why we have a different concept for each. Um, Weight and mass are proportional, and that they're not the same is really just a matter of what they're doing. We have different ideas about what the mass does. One of them is it acts as this gravitational charge. It's what couples you to gravity so that gravity can pull you down. And the other thing that it does is, we'll find this out later, it has some sort of inertial property to it. So, what are we going to do here? Well, we're going to talk a little bit about this weight, about how you can scientifically discover something like this, right? So, what we're going to talk about are operational definitions. And the operational definition is weight measured by a scale. And originally, this would just be a balance scale, right? So you'd say, okay, I have so much stuff, right? So I've got these little weights over here. And then you bring your stuff in there. Let's say you have, gold ore, like that, big pile of it. And we'd put my known weights over on one side and your gold ore on the other side, and we bounce them out to figure out how much of each we had. We may have said this isn't really what people did most of the time. Most of the time they just used the same volume every time for the same kind of quantity and just sold things in the different quantities that were available for the different stuff, different things. Weighing things is more difficult and less obvious about what's happening than a volume measurement. So it's a little less, it's a little more opaque, actually, as well as a little more difficult. So we're just going to use this as our operational definition. Weight is what a scale measures. That means originally we just, in science, say we don't care what the thing really is. First, we'll figure out a way to measure something that we think is like the thing that we care about. And then we can later on make refinements, right? We can do our measurements. We can find out if there's certain things that we thought were part of this measurement that shouldn't have been part of it, and so forth and so on. We make these refinements as we get a better idea about what's actually going on. But we always start with, instead of a definition that is sort of authoritative in science, we start with an operational definition. We just say, okay, here's how we're going to measure this. Let's do some experiments and see what happens. And then later on, somebody will clean up the data and they'll figure out what this important thing is that we're looking at. So the first thing we'll notice when we're playing around with these scales is that for the same material, the reading is proportional to volume. That's not too surprising to us, but if you have like a big cylinder like this and you have a half-size cylinder like that, right, if this is V and this is V over 2, the weight here is twice the weight over here. So that's not very surprising. That's very good. It means that the weight is sort of linear in the amount of stuff that we have. It makes it possible for us to actually use weight as a measure of things, say gold dust. So that's a pretty good start. The scale reading is proportional to volume as long as you have the same material. But if you have a different kind of material, it's different, right? So if you have copper, right, and you have the same volume of, let's say, gold, that same volume of the two things, the gold will weigh more. So if you put the same amount of gold here as you put copper over here, you're going to have a situation like this where the balance falls in this direction. The gold is heavier than the copper. That's okay, that's good. That's sort of the way things happen. But what we find is that if we take the same volumes of different materials, the ratios of the weights for those two materials is always going to stay the same. So if I take my original cylinder and take two of those half cylinders, these are always going to balance. It doesn't matter if this is made if these are made of gold, or if this is made of gold and this is made of gold, then this will always happen. If this is made of copper and this is made of copper, this will always happen. But it's not going to be the same if you mix copper and gold. But a cylinder of twice the height made out of the same material is always going to have, and the same cross-sectional area, will always have the weight, twice the weight of this guy. Always happens. So this equals 2 times that is always true. So that's true even though I take the same volume of copper and the same volume of gold, the gold always weighs more. So that's something else we learned from it. So this is going pretty good. We have a good idea here that the weight is proportional to volume. And it could be proportional to anything else that's also proportional to volume. So it depends on what happens with the different materials. Probably that's got something to do with some material property, because the different materials have the same ratios of the volumes, but the same volume of two different materials is not the same weight. And the strangest thing is that there's a slight difference. It's pretty slight in general, but there's a slight difference in the gravitational field strength in different places on Earth. Here in Galveston, it's about 7.8 or 9.8 meters per second squared. In other places, it's in like Mexico City, I think it's 7.73 meters per second squared. There's something weird there. And this is really just due to non-uniformities in the Earth's surface, right? So those non-uniformities change the mass profile near a person and therefore change the weight eventually. But that's just a little bit of something there. This balance can't discern number 3. And it can't do that because whatever we're multiplying by, if we've got something on the left-hand side, it's the same thing as happening to the right-hand side. So this thing you can't tell with the balance scale. Oops. But if you're using the spring scale, something like this, then you can. You can figure that out from that spring scale. So our weight is going to be proportional to something that has to do with the density and the mass, or density and the volume, which is the mass, actually. So the weight is the mass times some number. That number happens to be the gravitational acceleration. All right. And that gravitational acceleration differs depending on your unit system. G is 9.8 meters per second squared in the SI unit system. In the imperial system, G is equal to 32.2 feet per second squared. Okay, so that's more or less what weight is. You start off with that operational definition, but we get to the point where we know that weight is this thing that's proportional to the mass. And that thing that's proportional to the mass is very important for our calculations.